Okay, so in the 8 minutes that we have left, let's just at least give the gist of what boosting is. Boosting is one of the most famous algorithms in machine learning, and for good reason. Boosting is a shockingly accurate algorithm. And it actually comes from a different origin than bagging, and it's actually interesting to compare the two. Boosting is a great testament to the power of theory. In fact, the guys who invented this won this Kanellakis Prize for the best theory with real applications. Right? You can win lots of awards for theory that looks pretty but never made a difference to anybody's life, right? But there is this very prestigious award for theory that actually made a big difference. And boosting is a golden example of that. Because what happened with boosting is that boosting was invented as a way to prove a theorem. People were not thinking of coming up with a better new machine learning algorithm when they invented boosting. It was this guy called Rob Shapiro. And there was this problem that the founder of one branch of, actually Leslie Valent, who just won the Turing Award last year. He and one of his students, Mike Kearns, formulated this question. This is the kind of question that theorists think of that often winds up having very important consequences. Their question was, what is the relationship between weak learning and strong learning? Weak learning is my learner is just slightly better than chance. So a weak learner is a learner that is 50 plus epsilon% accurate, okay? Assuming the base rate is 50%, okay? And the strong learner is a learner that's 100 minus epsilon% accurate, right? Now, what you would like to have, of course, is a strong learner, right? What you have most of the time is a weak learner, right? And their interesting theoretical question is, are the two equivalent, right? Just like, is P equal to NP, right? And their suspicion was that, no, they were not equivalent, right? I mean, just because the learner is weak, just because you can learn slightly above chance, surely doesn't mean that you can learn almost, with complete accuracy, right? And then, this other guy, Rob Shapiro, came along, and he actually proved that weak and strong learning were equivalent, which was, a big surprise. He proved that if you have a learner that is 50 plus epsilon% accurate on any distribution, and that is the key condition, it has to be 50% accurate on any distribution of the instances in space, then you can, boost, and hence the name boosting, that weak learner into a strong learner, right? And this is an amazing thing to have, right? You have a learner that is only slightly better than chance, and by putting into this magic machine called boosting, you get a learner that is almost 100% accurate. But, he was a theorist, he proved his theorem, made a big splash and went home happy. Right? That was part 2 in this story. Part 3, another guy, these were all at different universities, over a span of a few years, called Yoav Freund, and it was Freund and Shapiro who won this award because they both contributed. He came along and said, maybe I can turn this into a real algorithm. And now the version of boosting that Rob Shapiro had was like a very ugly thing. Right? No one would want to use that. And in fact, it wasn't very good in many ways. So what Yoav did was he found a way to turn that into like a good, high-performing algorithm. So there were all these steps, and then the final step, which in some ways is the funniest one, is that these were still just theorists, right? What they did was prove theorems for a living. They proved a bunch of things about this, but then they were by this point they were at Bell Labs. Right, the famous Bell Labs. But these were the decaying days of Bell Labs when AT&T was, going downhill. And they were starting to be under pressure to show that they could do something useful with their theory. At which point, there was this contact between the theoretical and the empirical machine learning community, and they were like, oh, why don't we try this on these data sets in these, repositories, the famous UCI repository that people have been trying their algorithms. Let's try boosting on this and see what happens, right? It's not that hard. We can do that, right? They probably couldn't build a big system, but 100 lines of C code they could put together. And then they run it, and that's when their jaw dropped. Because these were data sets where people had been struggling to get 1-2% improvements in accuracy for 10 years. And they were getting 5-10% improvements in accuracy just like that. And the rest is history, as the saying goes. So, what is the boosting algorithm? Right? The boosting algorithm is a very clever idea. It's similar to bagging in some ways in that what you have is you learn many classifiers and then you vote over them, but the difference is that now there's going to be the examples are going to have weights. I'm still going to, it's similar to Wagon in that I generate different classifiers by learning on different variations of the training set. But now the variations of the training set are not random. They're designed. Because if you think about it, is it that really the best thing that I can do in order to generate different classifiers, just randomly generate different training sets? How about after I've learned my first classifier, what I do is I cleverly perturb the data to learn a classifier that is good where the first one was bad. This is what I want to do, right? I don't want to learn another random classifier. I want to see, like, where was the first classifier good? Well, that part of the space you can leave alone, right? That's fine. Where was that classifier getting things wrong? Let me now try to learn a classifier on that, and so on. Right? Now I learn my third classifier where the previous ones were bad. And so by the time I've learned 50 classifiers, if I've done this right, I've actually learned a very good classifier. In fact, if I could have 50 weak classifiers turning into one strong classifier by weighted voting among them. Okay, so that's the general idea in boosting. Very, very clever. Okay? So here's what's going to happen. I initialize with uniform weights, just like a normal learning, right? This is my full training set. It's not a bootstrap replica. It's my full training set, and all the examples have the same weight. And then I just go into the following loop. And each cycle through the loop is often called a round of boosting, right? So one of the parameters of the algorithm is going to be the number of the rounds of boosting that you want to do. And again, as a rule of thumb, 20 rounds is probably good, 50 is fine, 100 is too much, 1,000 is bad because you'll probably overfit. With bagging, you can never overfit. We will talk a little bit more about that next week. With boosting, if you take it too far, you can overfit. Okay? Because you can start learning, a classifier just for here and one just for there and overfitting the noise. Okay? So what is each round? Is you apply your learner to the weighted examples. Okay? So you need a learner that can take in a set of examples and weights for the examples. Not all learners can do this, but again, in another fortunate accident of history, remember, how we handled missing information in decision tree learning was by having fractional examples, right? 80% of the example goes to red and 20% goes to blue. Because of that, people like Quinlan already have algorithms that could handle, weighted examples, right? Because what is a fractional example? It's a weighted example. And so luckily, all they had to do was expose that and wrap boosting around it. If, however, you really, have a black box learner that doesn't handle weights and you don't want to modify it, there's a way to do this which works almost as well, which is, again, what you do is you do the bootstrap idea. You sample from the training set, but now it's with replacement, but now what happens is that instead of sampling with uniform probability, the probability is the weight. Okay, the weights all add up to 1, and you just create a training set where the examples that had more weight are more likely to show up, and will show up more times. Okay? And the ones with low weight maybe will show up once or 0 times. Okay? So even if your learner doesn't take in examples with weights, you can still do boosting quite successfully. So you apply your learner to your examples. Out comes a classifier, and now here's the key step. You look at which examples were misclassified and you increase their weight. Right? Now there's some very interesting theory behind this, but intuitively this makes a lot of sense, right? So the next classifier is going to focus on the examples that were bad for the first classifier. I'm going to increase the weight of those. And if there are some really difficult examples that the classifiers keep getting wrong, their weights are going to go up round after round after round until I'm really just learning a classifier for those examples until I'm guaranteed to succeed. And this is how you can get a strong learner out of a weak one. Okay? And we will see the details of and finally, you combine the models by voting as before, except that now, of course, the voting is also going to be weighted. The classifiers that were more accurate have more weight than the ones that were less. Again, this makes sense, right? Why make a uniform vote when some classifiers are better than others? Okay? And next week we will look at the details of boosting, and then talk about some other models, some methods, and do some learning theory. Okay? And in the meantime, have fun with your span classifiers and so forth.